I have two numbers being multiplied together here. There's 4 and x. Those two numbers are being multiplied together. So I want to write it as two separate logarithms, but addition of two separate logarithms. So log base 3 of 4 plus log base 3 of x. That's the idea with the expansion problems here. Now, when we get that part done, we do also want to check and verify that log base 3 of 4 can't be turned into a nice simple integer value for us. So I could say log base 3 of 4 is question mark. 3 to the question mark equals 4 when I change the form. And I know like 3 to the first is 3. 3 squared is 9. So 3 to the question mark, we know question mark is going to be somewhere between 1 and 2. We just don't know what it's going to be. And there's not really an easy way to find it out for this particular problem. So thankfully on this one, we can't simplify log base 3 of 4, so we can just leave it as that. Log base 3 of 4 plus log base 3 of x. And that's the expanded logarithm. Okay, that's what I mean when I say expand each logarithm. And that's what we did on the homework last night too. Problem 2, natural log of 15x, natural log of 15 plus natural log of x. That's the idea, right? And it is two separate logarithms, addition of two logarithms instead of multiplication inside of one logarithm. Problem 3, now it's a division problem. So for division, we do subtraction instead. Natural log of 12 minus natural log of 5. That's how we would write a subtraction problem instead. Because of the division. That was the quotient property we talked about yesterday. All right. Any questions so far on these three warm-up problems, the first three?
Wouldn't 3 be ln 7?
No, it would not be natural log of 7. Great question. You cannot actually do this like an actual addition and subtraction problem. It would just be, because it's not 12 minus 5 equals 7. It's 12 divided by 5 inside the single logarithm. So that's why we can't simply say that. That's a great question though. If I had one that was like, let's say natural log of 12 minus natural log of 3, that's technically natural log of 4. You following, Aaron? That's weird, right?
Yeah.
Why is it 4? Because it's 12 divided by 3.
Yeah,
sorry. And 12 divided by 3 is 4. No, that's okay. I'm just explaining why it wouldn't be 12 minus 5 equals 7. That's a great question because it's a really good common mistake that a lot of students could make. So we want to catch that. So that's great that you brought that up because I didn't even think about that until you mentioned it. Okay, so awesome. Okay, so next one, it has 3 numbers. There's a 5, an x, and a 6. And it's log base 10. We don't need to write log base 10, but we can say log of 5 plus log of x minus log of 6. That's how we'd want to write this one.
So wait, so when there's no number, when there's no base number in the log, it's 10 and not 1?
When there's no base number, the base is 10, yeah. So this is technically log base 10. All right, theoretically.
Why is it not 1? Because usually, like when there's no 1 there, we just assume that it's 1.
Yeah, it's 10 just because that's how, when logarithms were created, they decided to do a log base 10. That's the best answer I can really give you. Because it wouldn't be log base 1 because think about if it's a 1 and you wanted to write log base 1 of 5 equals question mark, it's going to be 1 to the question mark equals 5. It's impossible to raise 1 to any number to get 5 because 1 raised to any number is still going to be 1. That's why it's not base 1. Okay. Problem number 5 is log base 5 of 1 minus log base 5 of 5. And these ones, again, we want to double check. So, for example, I can check log base 5 of 1 equals question mark. That's 5 to the question mark equals 1. That means the question mark has to be 0. So this is really 0 minus log base 5 of 5 is 1. So this whole thing simplifies to -1. That's kind of a weird one because you can rewrite both parts. You might be able to see it as well at the very beginning as log base 5 of 1/5 equals question mark. Because then you could rewrite it as 5 to the question mark equals 1/5. And then the -1 might make sense to you. But if you've struggled on those fraction problems on the previous assignments, this is another new way you could do it and say, I can write this as two separate logarithms, and those are easier numbers to deal with because I know log base 5 of 1 is 0. I know log base 5 of 5 is 1, so I get 0 minus 1, and I got -1. So that's another way you could attack these types of problems, which is kind of cool. All right, last one here, log base 3 of 7xy. Log base 3 of 7 plus log base 3 of x plus log base 3 of y. Just three numbers being multiplied, so it's three logarithms being added together. That's how we can write it in expanded form. Okay. Today, the first thing we're going to talk about is the power property. It's the third property of logarithms. There's three properties total. We talked about two of them last time. The product property, which was two numbers being multiplied together. You can write them instead as two separate logarithms being added together. The second property was the quotient property. Two numbers being divided in a single logarithm can be written as two separate logarithms being subtracted. And then the last one, the power property, log base b of m to the n power. This is a new one for us. But this one, you can actually take the n and move it out front and multiply by the logarithm. Now, yesterday we tried to prove the other two, the product property and the quotient property, using graphs, and we could see equivalent graphs that were translated up and down. Today I'm going to use an equation to prove the power property. We're going to do one example on the left side using numbers. And whatever I do on the left side, I'm going to do the exact same thing on the right side using only variables. So the first thing I want to do is change forms. It's technically log base 10 of x squared right now. So I can rewrite this as 10 to the y power equals x squared. And that means on this side, it's log base b, it's going to be b to the x power equals m to the n. That's the first step. The next step, basically I want to get the variable on the right side all by itself. So it's an x and an m. So I want to root both sides. That's the next step. So on the left side, I can say, let's do square root of 10 to the y equals x. And on the right side, I'm going to do the nth root of b to the x equals m. Nth root because it was to the nth power. Square root on the left side because it was to the second power. I'm going to rewrite that radical as an exponent. Technically, it's called rational exponent form. So I can say 10 to the y power to the 1/2 power, b to the x power to the 1 over n power. And then I'm going to simplify. This is using properties of exponents that we talked about. I can rewrite this as 10 to the y over 2 power equals x, b to the x over n power equals m. Again, whatever happens on the left side, I'm doing the exact same thing on the right side, but with variables instead. So now I've got x by itself. I've gotten rid of that exponent. On the right side, I've got m by itself. I've gotten rid of that exponent. Now I'm going to change forms again. So we'll say step 1, 2, 3, 4. Step 1, 2, 3, 4.
Does that say 10 to the y over 2?
Yes, 10 to the y over 2, exactly. Step 5 is change forms again. Now I can write this as, what is it going to be? Oh, base 10, so it's going to be log base 10 of x equals the exponent y over 2. And over here, it's going to be log base b of m equals the exponent x over n. The final step, step 6, which I'm out of room over here, unfortunately, multiply both sides by 2. I want to get that y by itself again. And I get 2 times log of x equals y. Over here I get n times log base b of m equals x. And the key here is that this 2 log of x looks exactly like it did when we started, except the x is moved from the exponent to in front of the logarithm. And then the n log base b of m equals x. That's what we saw up here, n times log base b of m. So that's the whole idea with this type of problem. Sorry, I went through this pretty fast. I'm going to zoom out just a little bit here. I'm never going to ask you to prove these theorems or these properties, okay? That's not part of the course. I'm just showing you this is where it comes from, okay? That's the idea. But again, I'm never going to ask you to do it, okay? I'm just showing you today. This is where the proof comes from. That's the idea, that you have two problems that look very similar, but that's it, okay? From now on, as long as you have the three properties and you know how to use them, whenever you have an exponent inside of a logarithm, you can move that exponent out front and multiply it by the logarithm. That's what I want you to know how to do, okay? Step 6 was multiply both sides by 2. Okay. So the steps say change forms. That's right now. First thing you could do is you have this 4x to the 11. You could just start by saying let's change forms. And that means we rewrite it as log base 4 of 11 equals x. Perfect, we've got the x on one side by itself. That's exactly what we want. Then we can plug into calculator and solve. That's the first method. There's just one problem with that, is some of our calculators don't have the ability to plug in log base 4. Because your calculators either plug in log base 10 or they plug in natural log, which is log base e. Like if I were doing it on my phone, for example, I can flip it sideways on the calculator and I can do log base 10, log base e. And my calculator will actually say log base 10 on it and natural log. Those are the only two functions I have on my phone. If I have an old TI-84, like in my classroom, I have about 10, 12 TI-84s. I can only do log base 10 or log base E on those, natural log on those. I can't do anything else. So that's why you have to be careful with how you do these types of problems. So what you want to do then is you want to be able to use the other method, which I'm going to call the log both sides method. That'll be important as well. And we'll also talk about something called the change of base formula today. So you can change the base of any logarithm to put it into your calculator. So that's the first method. Plug into your calculator and solve. If I plugged this into my calculator, I would get x equals approximately 1.73 because I'm rounding to the nearest hundredth. If I wanted to check that, I can. The way you double check these algebraically is you just go back to the original equation and say 4 to the 1.73 equals 11. I round it up a little bit, so when I plug it in, I make it a number slightly higher than 11 when I put it in. But it should work out to give me 11 equals 11, and that's how I would double check my answer. Now the other method that's going to help us put this into a lot more calculators is the log both sides method. What the log both sides method says is we take the original equation and just think about it straight up algebraically. Instead of doing this changing forms thing, if that's really confusing for me, I'm not good at changing forms. I like this log both sides method because it's very algebraic in nature. Because on any equation, you can say, I want to add 7 to both sides. Because the equation stays balanced as long as I add 7 to the left side and I add 7 to the right side, it's going to stay balanced. Same thing happens with logarithms. I can say, let's take a logarithm of both sides. Log base 10 of 4 to the x equals log base 10 of 11. I'm going to do log base 10 because that's one I can put in my calculator. So this is the second option. I'm going to log both sides. And then I'm going to use the power property because I have this exponent 4 here or this exponent of x here that I want to drop out in front. So now I can rewrite this as x times log base 10 of 4 equals log base 10 of 11. Now I have x times log base 10 of 4. How do I undo multiplication to get x by itself?
Division.
Exactly. So the last part is I would divide both sides, again, keeping the equation balanced, by log base 10 of 4. And what happens is on this side I get divided by log base 10 of 4. On this side I get divided by log base 10 of 4. Log base 10 of 4 divided by log base 10 of 4 is 1. So I'm just going to end up with x on one side. On the other side I get log base 10 of 11 divided by log base 10 of 4. And you have to practice putting these in your calculators. If I'm using my phone, for example, this is an iPhone. I put in 11 and then I push the log base 10 button. And it's going to give me some weird decimal answer. And then I can say divided by 4 and I push the log button again and there's the log base 10 of 4 and then I hit equals. And I get 1.7297158. It's really important that whatever calculator you guys are using, you know how to put it in so you can get your answer out properly. And again, we round it to the nearest hundredth, 1.73. That's the other method you can use. I have to do the change of base formula if I'm using my phone, for example. All right. Otherwise, if I'm using a calculator, maybe I'm lucky and my calculator can let me put any base I want into it, but a lot of them don't. So you just have to be able to change the base. And we'll talk about something called the change of base formula here in a second too. All right, so that's the first problem. I showed you 2 methods for doing it. You can do the change forms method, or you can log both sides. All right. The second problem here, 10 to the 3x plus 4 equals 9. I want to log both sides, but I can't do it yet because of this plus 4, this dang plus 4. I got to get rid of that first. So my first step is going to be subtract 4 from both sides. And now my new equation is 10 to the 3x equals 5. Now I'm going to log both sides, or quote unquote change forms. In this one, if I log both sides, I'm going to get log base 10 of 10 to the 3x power equals log base 10 of 5. I can use the power property to move that 3x in front of the logarithm. 3x times log base 10 of 10 equals log base 10 of 5. Log base 10 of 10 equals what? Equals 1. Log base anything of that same number is 1. So log base 10 of 10 equals 1, so I end up with 3x times 1 equals log base 5, or I could just say 3x equals log base 10 of 5. And then the last step to get x by itself. So I'm going kind of fast again. Sorry, I apologize. I'll slow down. Last step to get x by itself, I'm going to divide both sides by 3 using my algebraic techniques here. So technically the exact answer I would have written down is x equals log base 5 divided by 3. Always good to show your work to get to this step first and then plug it into your calculator, because if you make some type of error on the calculations, at least I see that you have the exact answer and then it was just a calculator error at the end. So I do 5 and I hit log base 10 and then divide it by 3. And I get x equals approximately 0.23. Make sure you double check that answer. Okay. A second way you could double check the answer is you could actually graph it. Okay. So log base 10 of 10 is 1 because anytime you have a log and its base, so for example, this is log of 10, if we said equals question mark, since it's base 10, you'd say 10 to the question mark equals 10. Anytime a log and its base match, log base 5 of 5 equals question mark, you get 5 to the question mark equals 5. Log base 3 of 3 equals question mark, 3 to the question mark equals 3. So the question mark in each of these cases would be 1. That's why log base 10 of 10 is 1. Okay. Okay, so 10 comes from whenever the log doesn't have a base, it's assumed to be log base 10. Whenever a logarithm doesn't have a base like this, it's assumed that we're going to use base 10. Okay, and I want to use base 10 because that's what I can put into my calculator when I don't know when I want to change the base. Okay, that's why I choose base 10. All right. This part down here just says simply, why couldn't we just log both sides as our first step? And the reason is we want to isolate the base first. I can't do it before because if I have plus 4, then I would have to do a logarithm of the 10 to the 3x, a logarithm of the 4, and a logarithm of the 9, and it gets really messy really fast because now I have logarithms being added together and stuff like that. So that's the idea. Okay. So yes, thank you for answering that question. It's always going to be assumed it's base 10 if there's no base written down. If there's a base written down, use that base. If there's no base written down, we're going to say base 10. Okay, that's a great description there. Thank you. Okay, I have 3 problems here. I want you guys to try these 3 problems now. Solve each of these equations round to the nearest hundredth. Okay, and I'm gonna give you a couple minutes to work on it, and then we'll start going over it in just a minute here. Whenever we're solving a logarithm, we can use any base we want. We can take the logarithm of any base we want on both sides. Okay, it doesn't matter which one we use. That's the nice thing. So when we're doing a logarithm, I could do this as log base 10 of 2 to the x equals log base 10 of 5. And then the x drops out in front, and I get times log base 2 equals log base 5. And then I divide both sides by log base 10 of 2, and I get log base 10 of 5 divided by log base 10 of 2. Put that in my calculator, I should get the exact same answer. It doesn't matter. There's a third way I can do this. These are the 3 methods I would recommend using. Any one of these 3 is fine. I would use log base 10 or natural log, which is log base e, because those ones I can put in my calculator easily. The third one I would do is depends on whatever the base is in the problem. I would do base 2, to be honest with you. Log base 2 of 2 to the x equals log base 2 of 5. And now the x drops out front. Why do you think I chose log base 2? What's going to happen?
Log base 2 of 2 is 1.
Log base 2 of 2 is 1. Exactly. You've got it. So I've just made that simpler because now I've got the x by itself on one side. On the right side, I have log base 2 of 5. If I have a calculator where I can put log base 2 of 5 into it, awesome. Do it. All right, you can use this method right here. I did the log both sides still, but I chose strategically base 2 to eliminate the log base 2 of 2, and then it saves me a step later on in the process. I can do any base I want when I'm solving for logarithms. So one more time, we're going to hit it again last time. I can say, let's do log base 317 of 2 to the x equals log base 317 of 5. Why not? I can do it. It's perfectly fine. Is it going to get me closer to solving the problem? Not really. It actually makes it a little more complicated, but I can still move the x out in front. I can divide both sides by log base 317 of 2. And now I'm stuck again where like, well, if I don't have a calculator that lets me put this into it, then I'm stuck. But I can choose any base I want, but I want to choose a base that makes sense. So the 3 bases that make sense are either log base 10, natural log, which is log base e, or whatever base is being represented at the start of the problem. In this one, it's base 2. Any base you want. Okay? So what do you mean you can remove only the x and keep the 2? I'm curious about that question.
Well, on the example that you did, you had on kind of the far left, it was log 2 and then raised to the 2 of x.
It's not raised to the 2 of x. It's log base 2 of 2 and then to the x power. So only the x is being raised. Sorry, it's just horrible handwriting, but it's still this same exact problem.
It's okay.
Right here.
So if you had, so you can just use the base in another equation?
You can use any base you want, and it's the, so I did 3 examples here. One of them was with base 2, one of them was with base 10, and one of them was with base E. So
Okay,
I even did a 4th example with base 317, but that one doesn't make sense to use because it doesn't help us get closer to solving the problem ultimately, or any faster, I should say.
Okay, thank you.
You're welcome. So for problem 2 here, instead of choosing log base E or log base 10, I'm going to choose the third option. What base should I use then if I'm not going to use base E or base 10 on this problem 2? What base is being represented by the problem already?
7.
7, exactly. So I can do log base 7 to the 9x power equals log base 7 of 15. And then the 9x drops out front, and I get log base 7 of 7 equals log base 7 of 15. Log base 7 of 7 is 1, so now I have 9x equals log base 7 of 15. Now, like I said, there's something called the change of base formula, which is right down here. We're going to skip ahead to that right now before we get to the third problem. And what that is saying is I can take any logarithm, like log base c of a, and I can rewrite it with a base. We'll do log base 7 of 15 at the same time, log base c of a. And I can rewrite this as, like, let's say log of 15, or log base b of 15. I'm just going to say log of 15 divided by log of 7. Over here, we'll say log base b of a divided by log base b of c. I can change to any base I want, whenever I want, which is pretty cool. But the two bases that make the most sense for b, because are the ones that I can put in my calculator, base 10 or base e. And base e is the natural log. So technically I could write this as log base 10 of a over log base 10 of c. Or I could write this as natural log of a over natural log of c. So log base 7 of 15 I could write as log of 15 divided by log of 7. Or I could write it as natural log of 15 divided by natural log of 7. Those are the two ways I could rewrite this. This is called the change of base formula and allows you to approximate any logarithm using a calculator that doesn't let you do any base you want, only lets you do base 10 or natural log base. And again, I'm going to go back to another example I had, but I could technically have log base 7 of 15, and I could rewrite this as log base 317, I'm going to use that number again, of 15 over log base 317 of 7. But that doesn't help me get closer to putting the problem in my calculator. If I can't put log base 7 of 15 in my calculator, why would I change it into something more complicated? Legally, I'm allowed to do that. That's an okay math thing to do, but it doesn't get me closer to solving it. Does that make sense? Hopefully. Maybe? Yeah, that's the idea here. I can change to any base I want. I can log both sides with any base I want, but I want to choose strategically something that's going to help me put it into the calculator more easily. So for number 2 here, I had log base 7 of 15. I end up getting like 1.39. 9x equals 1.39. So then I have to divide that answer by 9 to get my x value of 0.15 when it's rounded to the nearest hundredth. That's how I would get my answer for problem 2 there. And again, I can change that base if I need to and rewrite it as like log base 10 of 15 divided by log base 10 of 7, so that way I can put it in my calculator. All right, last problem here, example 3. I'm going to start by adding 7 to both sides. I got to isolate the base before I can change the forms. One thing that's really tricky about these particular problems, though, you're going to see this on your homework tonight, I'm warning you right now, is the 4 being raised to the negative 3.3 x power. Is it part of that base? And the answer is no, it's not part of that base. So what I have to do is I have to divide both sides by 4 before I change forms. So I get e to the negative 0.3x equals 5. Now I can change forms, or I can log both sides. And in this case, I want to do the natural log because natural log happens to be log base e. So that's going to save me some steps here. I drop the negative 0.3x out in front, and I have negative 0.3x times natural log of e, or log base e of e. That's going to become a 1. And then that goes away. I'm left with negative 0.3x equals natural log of 5. Now I can put natural log of 5 in my calculator. And then I'm going to divide by negative 0.3. And I get x equals 5.36. Okay, that's the idea for problem 3 there. Okay, so that covers the ideas of the property of logarithm where we can move the exponent out in front. And also today we talked about just the idea of changing to any base we want. All right. Strategically for problem 2, I chose to do log base 7 because the base was 7. And then that got me a log base 7 of 7, which turned into 1. It just makes it a little easier in the solving process. So it just depends on each problem in particular. Okay. Yes, thank you. The last one should be negative. Thank you very much, Allison. Good catch. Should be negative 0.536. Yeah. All right. So last thing with this change of base formula, easy way to remember it is I always think about the base of the logarithm goes to the basement of the fraction. Or the denominator of the fraction, right? So when you're changing forms, that's how you can remember it. The base goes to the basement. All right. Now, the last thing I'm going to ask you guys to do is we'll do one example, and then I'm going to ask you guys to try this yourselves. Again, practice putting it into your calculators so you know you're getting the right values. First, we're going to look at log base 3 of 8. And it says step 1 should be to guess at it. And what I mean by that is I can say log base 3 of 8 equals question mark. So 3 to the question mark equals 8. Well, I already know that 3 to the first power equals 3. 3 to the second power equals 9. So I know that question mark is going to be somewhere between 1 and 2. It's got to be an exponent between 1 and 2. So we can kind of guess and say, I think question mark is going to be, I don't know, nearest hundredth, so like 1.80, maybe 1.90, I don't know, that's just guessing to the nearest hundredth there. But it's going to be probably somewhere around there because 8 is closer to 9 than it is to 3, so therefore the exponent is probably closer to 2 than it is to 1. That's kind of how I came up with my educated guess there. Now, I can use the change of base formula to try it. It was log base 3 of 8. Using a common logarithm, log base 10, I can rewrite that as log of 8 divided by log of 3. And again, I want to use this guess and check method because if I guess that it's 1.8 or 1.9 and I do log of 3 divided by log of 8 on accident, I'll get a number that's way off of 1.8 or 1.9. It'll be like 0.4 and be like, oh, okay, I must have done that backwards. I must have set it up incorrectly. The other method, natural log of 8 divided by natural log of 3. And then the final step is we put it into our calculator. So I do 8 natural log divided by 3 natural log, and I should get something like 1.89. So it's fair to say that log base 3 of 8 is rounded to 1.89, which fits our guess. If I did log base 8 of 3 on accident, I probably would have gotten like a 0.4, so I would have known I put it in incorrectly. All right, last 4 problems. I want you guys to, again, practice putting these into your calculators. Make sure you're doing them the correct way. I'm going to put the answers up in just a second here. Okay. I got the 4 answers up here so you can double check them. I know I went a little fast there, but I just hope you've got this generally figured out. I just want to make sure on the first couple, make sure you're putting it into your calculator correctly. All right. So if you're doing this on your phone, and you're using the calculator on like an iPhone, for example, just turn the phone sideways and it'll say the log, it'll have the log buttons on there. And you're gonna wanna type the number first and then hit the log button. So I would say 8 and then hit log. It's gonna give you a number, and then I'm gonna say divided by 5, hit the log button again, there's the log of 5, and then hit the equal sign, it gives me 1.29. So again, that's why it's important whenever you, that's why it's important that whenever you're practicing these, you know which calculator you're using and how to use that calculator. Okay. For your assignment tonight, assignment 15 over the weekend, problems 1 through 4, use the change of base formula to evaluate each logarithm. So more practice like what we just did. Problems 5 through 8, those are the most important ones, the solving. Make sure you're good at solving these types of problems. Isolating the bases first. And then problems 9 and 10 are expanding the logarithms like what we did on the warm-up. Problems 11 and 12 are condensing them, which is like putting them back together. So you're doing the reverse properties of logarithms. And that's going to be helpful when we start solving logarithms on Monday. We need to know how to condense equations first. That's really important there. All right, so that covers everything for today. If you want to stay on and work on the assignment,